You know that feeling when you're using a large language model and it just seems to learn something new right in front of your eyes? You give it some new facts, a new rule, and it just gets it instantly. It really does feel like magic. But today, we're going to pull back the curtain and dig into the mechanics of how it actually works. And this really is the central puzzle, isn't it? We're always told that AI learns through this long, grueling training process that takes massive data sets and tons of time. So how in the world can it pick up a new skill on the fly with literally zero training? I mean, it seems completely impossible. Okay, let's just try a quick example. I can tell a model, a zorp is a shiny purple cube. And then I ask, what shape is a zorp? And boom, it answers, a cube. It didn't need thousands of examples, it didn't need hours of training, it just figured it out from the tiny bit of context I gave it. So this thing that feels like magic, well, it actually has a name, in-context learning, or ICL for short. It's the AI's ability to figure stuff out at what researchers call inference time, which is just the fancy term for the exact moment you ask it a question based only on the info you put in the prompt. And this is where it gets really wild. Traditional AI learning is slow, it's permanent, and it needs a mountain of data. In-context learning is the total opposite. It's instant, it's temporary, and it only needs a handful of examples. So what gives? What is really going on here? Yeah, that's the billion-dollar question. Is the AI genuinely learning the way a person does? Or is this all just some incredibly clever trick happening deep down inside that complex black box? Well, to find out, we've got to pop the hood and look inside the machine. All right, so let's dive into the mind of a transformer model. A group of researchers at Google wanted to play detective and pinpoint exactly where in the AI's brain this in-context learning was happening. Okay, here's a super simple breakdown. Your prompt goes into the system. First, a component called the self-attention layer reads all the words and figures out how they relate to each other. Then it passes that information over to the MLP, which stands for multi-layer perceptron. Just think of it as the model's main processor. And finally, out pops the answer. So the investigation zeroed right in on that handoff between those two components. The researchers figured out that the secret wasn't in one part or the other, but in how they work together. This is where the magic really happens. And this led them to a really cool breakthrough theory. They called it implicit learning. And the basic idea is that the model isn't just passively reading your prompt, it's actively using it to change how it thinks. I love this analogy because it makes everything just click. Picture a world-class musician. Okay, they already know music theory inside and out, they've completely mastered their instrument, and they can play thousands of songs from memory. Now you hand them a brand new piece of sheet music. What do? They don't go back to music school. They don't retrain for months. No way. They use all that existing knowledge to instantly interpret the new notes on the page and play the song perfectly right there on the spot. That performance is just a temporary adaptation. And that's a perfect picture of what the paper found. The researchers discovered that the combination of the self-attention layer and the MLP allows the prompt, that's our sheet music, to implicitly modify the model's internal connections, or its weights, for that one specific task. So, let this sink in, because it's the crucial point. The prompt you write isn't just data being processed. It's actually a set of instructions. It temporarily reconfigures the AI's internal network, telling our expert musician exactly how to play this one new song. It's a temporary tune-up, not a permanent upgrade. Okay, so that's a brilliant theory, but you know how it is in science, you gotta prove it. So how on earth could they be sure that this implicit rewiring was actually happening? Well, they designed a really elegant experiment to find out. What they did was actually pretty clever. First, they gave the AI a prompt with context, the normal way, and recorded its answer. Then they took the same AI, gave it no context at all, but, and this is the cool part, they manually went in and changed its internal MLP weights using the exact mathematical formula their theory predicted. Then they just compared the two answers. This was the moment of truth. If their theory was right, the answers from both scenarios should be exactly the same. The rewiring that the prompt was supposedly doing naturally should be perfectly copied by their mathematical formula. And look at that. They were identical. A perfect match. As the paper's authors put it, the results were in remarkable agreement, which is basically scientists speak for, holy cow, it actually worked. Giving the model context produced the exact same behavior as manually changing its weights. So there you have it. Case closed. The mystery of in-context learning isn't some unknowable magic. It's mechanics. It's a predictable, mechanical process where the prompt you write provides the instructions for a temporary, on-the-fly update to the model's internal wiring. So now that we've solved the mystery, what's the big takeaway? Well, it fundamentally changes how we should think about what these models are doing every time we interact with them. First off, it means that the name in-context learning is actually a little bit misleading. The AI isn't acquiring brand new knowledge like a student cramming for an exam. It's not going through the same process it did during its original training at all. What it's really doing is showing off an incredibly powerful, built-in capability. It's reconfiguring its vast pre-existing knowledge to solve the specific problem you just handed it. It's an expert adapting, not a novice learning from scratch. All right, so let's just boil it all down real quick. 1. ICL works by making temporary adjustments to the model's internal network. 2. Your prompt is literally the instruction manual for those adjustments. 3. This is a mechanical feature, not a mini training session. And 4. It's the secret sauce that lets these models apply what they already know to totally new situations in a split second. And that leaves us with a really fascinating, kind of mind-bending final thought. If a machine can effectively rewire its problem-solving approach for every single question it gets, it forces us to ask a much, much deeper question. What is the true definition of learning? And are we witnessing the birth of an entirely new kind of it?